And what we now want to do is therefore to look at something about the properties and candidates for dark matter. And the first thing we can note is that dark matter interacts only weakly. Only weakly. I.e. gravity, which is a weak force, and possibly, but not necessarily, the weak force. I.e. not strong force, and importantly not EM. And there's actually a very nice picture which demonstrates this. This is something called the Bullet Cluster. It's a very famous galaxy cluster. It's actually a merging galaxy cluster. And so what has actually happened here is that two clusters have come across each other. So one's come through this way and the other one's come through this way. And in a galaxy cluster, you have some stars. Stars are really little point masses. They go straight past each other. So the stars go straight through because they don't interact. But the gas, which is most of the mass, it shocks. And so here, this red bit in the middle here, this is X-rays from hot gas that has shocked. So as this cluster merges, most of the matter has ended up in the middle as hot gas that's shocked. But there's a neat trick that people have used here to actually get a picture and understanding of what's going on. And that's something called weak lensing. And so there's three types of gravitational lensing. There's strong, weak, and micro lensing. And strong lensing, I can go all the way back up here now. When I look at this image of a galaxy cluster here, you probably can't see it terribly well, but if I zoom in a little bit, you can see these little arcs that sit in here. Another one down here. There are actually several around, also in here. This is strong lensing. So this is when you have light which comes past a strong source of mass, and eventually it's very distorted. You actually end up with multiple different lines of sight, giving you multiple images of a galaxy. That's called strong lensing. It's actually a really useful cosmological tool. We don't talk about it too much in this course, but if you look at general relativity, for example, strong lensing is very important. We'll talk about microlensing in a minute because that's also important for dark matter. But the idea of weak lensing is, imagine I have some background galaxy sitting here in the background. And then I have some foreground galaxies here. I'll just draw them badly. They all have some gravity, and then I'm observing over here. And so if I take some light from this galaxy, in principle, it just should do a straight line to me. But actually, as I go past these galaxies, what actually happens is that this light is slightly deflected one way or another. It sort of wobbles its way to me, very weakly deflected because gravity affects light. We saw that in lecture 2 when we talked about relativity. And so weak lensing changes the shape of background galaxies. And that change is dependent on the mass. So I can do a neat trick with this picture here, which is I can look at galaxies behind this, behind this area here. I can look at their sizes and their shapes, and I can do a sort of clever statistical trick to actually work out what the mass is in this cluster in front. And what you conclude is that all the mass of baryons is indeed here, but most of the mass in these clusters is in these blue areas here and here. So baryonic mass shocks, it interacts. What that really means is that it interacts electromagnetically. Dark matter interacts only via gravity. Now, I said earlier, possibly the weak force. And so that is the properties of dark matter that you're looking at. And there are, therefore, two classes of dark matter that you can think of. One of these comes from the particle physics crowd, and they're called WIMPs. That stands for weakly interacting massive particles. And they're basically elementary particles that we have not yet observed. And so there are things called axions, which you might think of, things called neutralinos. These are all complex elementary particles. They're sort of new physics beyond the standard model that you need to get them. But they are the particle physics ideas. And then on the astronomy side, and I have to say, there's a terrible sense of humour, because this was intentionally done in response to WIMPs. Astronomers proposed something called the MACHO, which stands for Massive Compact Halo Object. And these are astronomical objects that don't create light. So you might think of, stars make light, but not all stars create energy. In particular, if you have a white dwarf is just the remnant core of a star. It's no longer creating energy from fusion. It starts hot, but it cools. So it could be something like that. It could be a neutron star. These are the mass of the sun, but 10 kilometers across. Or it could be a black hole. And so both WIMPs and MACHOs, in principle, have the ability to explain what dark matter is. And they're very different because one of these, right, these things over here are elementary particles. They have masses of, 10 to the minus 26 kilograms or something. And these over here, well, they have astronomical masses, solar masses or more. So there's 60 orders of magnitude between them. So it's quite striking that we understand sufficiently little about dark matter, that we don't know whether it's something that's very, very light and very, very common. If it's at this end, the WIMPs, they're streaming through us in great numbers all the time, or something very, very massive, but very rare. So that's a big open question, but of course there are observational consequences to both of those things. So, there's a big question. Which is it? WIMPs or MACHOs?